This is SpaceTime Series 27, Episode 52, for broadcast on the 29th of April 2024. Coming up on SpaceTime, Stardust from a supernova confirms a new type of star. Good news for NASA with the historic Voyager 1 spacecraft finally phoning home. And New Zealand's Electron rocket launches NASA's new solar sail satellite. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Scientists studying a rare dust particle trapped in an ancient meteorite have found that it originated in another star system and came from a new type of star. A report in the Astrophysical Journal claims the tiny particle was created in an only recently discovered type of hydrogen-burning supernova, which exploded long before our solar system was even born. The discovery by Nicole Neville and colleagues from Curtin University was made after the authors identified grains with an unusual isotopic composition. Most meteorites that arrive on Earth are composed of material that formed in our solar system out of the protoplanetary disk which also formed the Sun and planets 4.6 billion years ago. But occasionally, such as with this sample, meteorites can also contain tiny particles known as pre-solar grains. These originate from stars which were born, lived and died long before the Sun came into existence. Clues that these particles are relics from other stars are found by analysing the different types of elements inside them. To do this, the authors used a technique called atom probe tomography. This analyses the particle and reconstructs its mineral composition at an atomic scale, revealing hidden information within. Neville says these particles are like celestial time capsules, providing a snapshot into the life of their parent star. You see, minerals created in our solar system have very predictable ratios of certain isotopes, that is, variants of elements with different numbers of neutrons. However, this sample has a ratio of magnesium isotopes that's very distinct from anything in our solar system. That means its origins had to be interstellar. The study's co-author, Phil Bland from Curtin School of Earth and Planetary Sciences, says the results were literally off the charts. The most extreme magnesium isotope ratio from previous studies of pre-solar grains was about 1,200, but the grain in this sample has a value of 3,025, the highest ever recorded. This exceptionally high isotopic ratio can only be explained by its formation in a recently discovered type of star known as a hydrogen-burning supernova. Hydrogen-burning supernovae are the remnants of a type of star that has only recently been discovered, at about the same time as the authors were analysing their meteorite sample. The atom probe has therefore provided a new level of detail, helping astronomers understand how these stars are formed. Bland says new discoveries from studying rare particles in meteorites are enabling scientists to gain fresh insights into newly discovered cosmic events well beyond our solar system. Bland says it's quite amazing to think that atomic scale measurements carried out in the lab in Perth could be linked to a recently discovered, previously unknown type of star deep in the cosmos.
This is the work that a former PhD student has done, Nicole Neville, and she was a graduate at Curtin University, both degree and PhD. What she's done here is look at very, very ancient meteorites, ones that are really quite well preserved, that not an awful lot happened on the asteroids that they come from in terms of the geology, and studied there are grains in rare meteorites that actually come from other stars before the solar system formed. So it's kind of the last trace of the precursor material that was the cloud of dust and gas that then the sun and the planets formed from. And what she's done is use these really amazing high-resolution techniques to study and found this one grain that is pretty unique, that is actually comes from a type of star that was only recently discovered by astronomical techniques. So it's really fascinating work.
So this type of star is called a hydrogen supernova. Tell me about it.
Yes. So it's really, we don't know an awful lot, actually. And so one of the things that we get from pre-solar grains is the ability to kind of complement the astronomy by establishing kind of details of the chemistry and the isotopic composition of what's going on in a star or what's going on in a supernova. You only get so much from astronomy, so being able to kind of have a little piece of that in the lab means that you can then tune a lot of your models about what's happening in those stars or in a supernova. And so it's crazy, but you can actually use 100 micron or smaller grains to give you information about galactic chemical evolution. So the thing that I'm fascinated by is really trying to get at, if you think of all of the sources for all of the ingredients that were there in the cloud of dust and gas that then contributed to the material in our solar system, one of those was one of these hydrogen-burning supernovae. And it'll be really fascinating now to find, all right, was that kind of local? Did that occur locally in our region of the galaxy just before or during accretion of those stars? Or was it like a previous generation? Was it kind of, a long time before, and that cloud had just kind of accumulated stuff from several previous generations of stars? So that's a thing now that colleagues can kind of dive into.
As the solar system moves through the Milky Way, we're currently in what's called a local bubble. And that local bubble is thought to have been created by a supernova explosion.
Right. And it's, I think the more that we are finding really about kind of how dynamic star formation was and planet formation, almost as like a complement of star formation. I mean, when I did geology at university 30 years ago, and at that time we didn't even know if there were other planets in the universe. And so, maybe the solar system is it. And then there was some work.
I still remember Pegasi 51. It's a favorite of mine.
Right, exactly. And so now our estimates are that there are probably more planets in the Milky Way than there are stars, which is just remarkable. And like you say, Stuart, the Milky Way as this like kind of dynamic environment where, we're in a bubble here of a supernova, and star formation is this really complicated, very dynamic situation. It's not like accrete one star in a quiet little place. There are dozens and dozens of stars accreting in and coming together in the same region and have close gravitational approaches to one another, and the disks around them can get stripped off and swapped. And the further we go, the more fascinating and dynamic that whole process is.
As we're talking, there's a growing body of evidence suggesting that our own sun and solar system were triggered into being by another supernova that just provided enough shock for a molecular gas and dust cloud to collapse.
That's right. And we don't know. It's a theory that's been around for quite a while, and every now and then, we get maybe a little bit more evidence for that, and then there's evidence against. But what we certainly know is that environment, like I say, was really dynamic. And you will have had stars that were forming and then were going through, and that were large and going through a life cycle that was much, much quicker, much faster than the one that our star is in. And now we can actually look at star forming regions and kind of, people have sort of tracked back stars that have come from a different region. So you can see how all those stars have kind of pinged off from their formation region. So there's kind of a whole other area of study now that is, like I say, is like the galaxy is a really dynamic system.
And these specific pre-solar grains that your team's been looking at, they have high levels of magnesium isotopes.
Right. And so the way that a long time ago, actually not that long ago, for most of my time as a planetary scientist, people would find pre-solar grains by basically dissolving an awful lot of rock and then just leaving the really hard, the really tough minerals that were pre-solar grains, that were diamond and silicon carbide, things that wouldn't react with acid. But more recently, over the last sort of 15 years or so, 20 years maybe, we've had techniques that are able to see isotopic anomalies in situ. It's like you have a microscope and you can see the variation in isotopes in a rock as you scan over an area in a meteorite. And what those anomalies are basically saying is, on a diagram of one isotope of an element versus another, everything in the solar system clusters around really a small area. It's like we've kind of exchanged all these elements with everything else over the history of the solar system, and now, there's very little variation. And you'll see these other grains that have tremendous isotopic anomalies that just you cannot get from anything occurring in the solar system. And that's how we identify a pre-solar grain. The ability to do it in situ and then to extract that material and then study that in detail is much more recent. And the stuff that Nicole is really doing is right on the cutting edge, both analytically in the techniques that she's using and in interpretation.
And that's where atom probe tomography comes in.
Exactly. And this is an amazing technique. So what happens there is you find a grain that you're looking for in a rock, and then you use a technique to basically sample a thin wafer. And by thin, I just mean, it's like tens of microns across, and then you shape that into a needle, which is even smaller, and then you put that into the atom probe, and a laser basically decomposes that. But as it's doing that, you are measuring both the position and the isotopic composition of each atom that comes off, or the mass of each atom that comes off. And so what you end up with is actually a 3D model of the position and composition of every atom that has come off this object. So you destroy this tiny needle in the process, but then you get an amazing kind of 3D model that you can kind of rotate on the screen, and you can see there is variation in a tiny area. You can actually see that in the model that you've generated. And that's what she's been really pioneering in the study of meteorites.
So the laser is evaporating the sample. Does it do it layer by layer or atom by atom, or does it go for the specific atoms first? Like it first grabs ones which have maybe fewer electrons or fewer neutrons?
Yeah. So it doesn't do that. It's kind of counting everything that comes off, sort of irrespective of
first come, first serve.
Exactly.
The fact that we're seeing so much variation in these pre-solar grains, it shows there's an awful lot of mixing going on in our part of the galaxy.
Absolutely. And I think this is part of when we get into the sort of the study, for planetary scientists and what is the nature of planets in our solar system, is that you can really only make these sort of objects after kind of multiple generations of star formation, where you're kind of building heavier elements in the atmospheres of stars and in supernovae. And so you actually need multiple generations of star formation, and then you accrete the material from the previous generation, and then you cook that up and to get an abundance of those heavy elements. So that kind of, generation after generation after generation, and mixing as well, is an inherent part of star formation and planet formation.
So it takes 280 million years for our sun and solar system to make one complete orbit around the Milky Way galaxy, but it isn't just going around the black hole, it's also going up and down through the width of the galaxy itself, through the disk.
Yes, that is true. We also migrate through spiral arms, which is fascinating, isn't it?
Well, the fascinating thing is the density of those spiral arms doesn't change as the stars move through them.
Yeah.
This is where dark matter starts to come into the whole thing.
Yes, exactly. And so, the idea that the galaxy that we see is really just one element of the galaxy as it truly exists. It's gorgeous. Yeah.
That's Professor Phil Bland from Curtin University's School of Earth and Planetary Sciences. And this is Space Time. Still to come, celebrations at the Jet Propulsion Laboratory after NASA's historic Voyager 1 spacecraft finally phones home. And New Zealand's Electron rocket launches a new NASA solar sail satellite into orbit. All that and more still to come on Space Time. There are celebrations at NASA today with vital communications restored with the agency's historic Voyager 1 spacecraft. The probe, which is the most distant man-made object in existence, lost normal communications with mission managers back in November when it suddenly started transmitting unusable gibberish instead of the usual data about its surrounding environment and the health and status of its onboard systems. Together with its sister spacecraft Voyager 2, which launched 2 weeks earlier, Voyager 1 was launched from the Cape Canaveral Air Force Station in Florida 46 years ago. Its launch date, September the 5th, 1977, and its mission was a grand tour of the outer solar system. You see, a few years earlier, astronomers had discovered that the planets were about to align in such a way that a spacecraft could use the gravity of one of the outer planets as a slingshot, flinging itself to the next planet, and from there onto the next, and so on. Amazingly, this would allow the two Voyagers to undertake a grand tour, visiting the gas giants Jupiter and Saturn. Voyager 1 would then head for the edge of the solar system, eventually becoming the first spacecraft to reach and explore interstellar space and the galaxy beyond. Meanwhile, Voyager 2 would continue its grand tour of the solar system, visiting the ice giants Uranus and Neptune, before it too would leave the solar system, travelling in a different direction. Voyager 1 is now located more than 24.3 billion kilometres away, well beyond the boundary of our solar system. It's been in constant communications with mission managers, reporting not just what the surrounding space is like, but also how its own systems are performing more than 4 decades into its journey. However, on November the 14th last year, Voyager 1 began sending unreadable data to mission managers at the Jet Propulsion Laboratory in Pasadena, California. Mission controllers could tell the 815-kilogram spacecraft was still receiving their commands and otherwise appeared to be operating normally. It took several months of inventive sleuthing, but technicians finally determined the problem was tied to one of the spacecraft's 3 major onboard computers, called the Flight Data Subsystem. It's responsible for packaging the science and engineering data before it's sent onto Earth. The team discovered that a single chip responsible for sorting a portion of the computer's memory, including some of its software code, had stopped working. And the loss of that code had rendered the science and engineering data unusable. Unable to repair the chip, the team decided to place the affected code elsewhere in the memory. Problem is, no single location aboard the spacecraft, remember it's 46 years old, and it took years before that to build, so you're talking about half a century here, no single place was large enough to hold the code in its entirety. So instead, mission managers devised a plan to divide the affected code into sections and store these sections in different places in the flight data subsystem. Now, to make this plan work, they also needed to adjust these code sections to ensure that they all still function as a whole. Any references to the location of that code in other parts of the flight data subsystem memory also needed to be updated. The team started by singling out the code responsible for packaging the spacecraft's engineering data. They sent that to a new location in the memory on April the 18th. Now, a radio signal takes 22.5 hours to reach Voyager 1 from Earth. Then there's another 22.5 hours for the return signal to come back to Earth. Needless to say, the wait was excruciating. But when mission managers finally heard the return signal from the spacecraft on April the 20th, they knew their modification had worked. For the first time in 5 months, they've been able to check the health and status of the Voyager 1 spacecraft. Now, over the next few weeks, the team will relocate and adjust other affected portions of the flight data subsystem software, and these include the portions that will start returning fresh science data to NASA. As for its sister probe, Voyager 2, well, it continues to operate normally. There are no problems there. And together, the 2 Voyager spacecraft remain the longest-running and most distant spacecraft in history. This is SpaceTime. Still to come, Rocket Lab successfully launches an Electron rocket carrying NASA's new experimental solar sail into orbit. And later in the science report, a new study warns that women with BRCA genes who get breast cancer within 10 years of giving birth are more likely to die. All that and more still to come on SpaceTime. Rocket Lab has successfully launched an Electron rocket carrying NASA's new ACS-3 technology demonstrator experimental solar sail into orbit. The flight from Launch Complex 1 on New Zealand's North Island's Mahia Peninsula will explore solar propulsion by deploying a CubeSat into orbit around 1,000 kilometres above the Earth. Called the beginning of the Swarm mission, it'll test the CubeSat's reflective solar cell's properties, where the pressure of photons from sunlight alone, comparable with the force of a paperclip falling on the palm of your hand, will be used to maneuver the satellite without engaging conventional rocket engines.
Stage 1 and Stage 2 tanks are pressed for flight.
High flow engine purge enabled.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Liftoff.
Beginning pitch over.
Stage 1 propulsion is nominal.
The beginning of the swarm has begun its ride to space with that clean Electron liftoff from LC-1. Electron's trajectory will take it up and over the South Pacific Ocean as it heads away from the launch pad. Our first mission milestone will be max Q, otherwise known as maximum aerodynamic pressure, which is the moment where Electron experiences the most amount of stress as it climbs through the atmosphere. We're coming up on that moment now and expecting to hear the call for max Q shortly.
Heat-free battery discharge nominal. Cleared max Q.
That is Electron clear through max Q, with the rocket now at 15 kilometers in altitude and moving at over 2,200 kilometers an hour.
Next up, Electron will perform 3 actions that are only seconds apart. The first is called MECO, or main engine cutoff, and this is when the 9 engines at the bottom of the rocket there shut off in preparation for the second step, and that move is called out as stage separation, when the first stage of Electron separates from its second and falls back to Earth. Now the third call out after separation should be second stage engine ignition, when the single vacuum optimized Rutherford engine fires up to maintain the mission's course to low Earth orbit.
15 seconds to staging.
Entered burnout detect mode.
MECO confirmed. Stage 2 ignition confirmed.
Stage separation successful.
There we go, that was MECO, stage separation and engine start on the second stage. Beginning of the swarm is now over 100 kilometers above Earth, past the Kármán line, and moving at more than 8,000 kilometers an hour. The next mission milestone is fairing jettison, or separation of the nose cone.
Fairing jettison is now complete. We dropped those 2 fairing halves early into the mission because they're not needed for satellite protection anymore now that we're through Earth's atmosphere. That dead weight is gone, and the mission is now a step closer to our first payload deployment at 520 kilometers.
Now, before deploying NASA's solar sail, the mission deployed South Korea's NeoSat-1 Earth observation satellite into a 520-kilometer high orbit. NeoSat-1's equipped with a high-resolution optical camera, which is paired with artificial intelligence in order to provide critical data for disaster relief.
We have a couple of minutes to go until our next mission milestone, and that will be the battery hot swap on the second stage, currently expected to take place at the T plus 6 minutes 20 second mark. Right now though, Electron's second stage is continuing along nicely to our target apogee of 520 kilometers for our first payload deployment for KAIST. This KAIST satellite is the first of up to 11 satellites planned by them, which will help to increase the program's observation rates of once every 2 to 3 days to 3 to 4 times daily.
Electron is still progressing smoothly through flight, and all remains healthy with KAIST and NASA's satellites. For NASA's payload, packed into this small satellite are composite booms that will unfurl once the payload is deployed, much like how a butterfly's wings emerge from its cocoon.
Following 2 months of subsystem checks and verifications, the CubeSat will execute a series of maneuvers in order to demonstrate potential attitude adjustments using nothing but the solar sails. The project's designed to test more cost-effective missions using solar cell propulsion for early warning systems, space weather monitoring, and exploratory missions to asteroids, destinations like the Moon and Mars. Now, solar cells have been tried in orbit before with varying degrees of success. These ones use new materials and deployable structures and are comparable in area to that of a small apartment.
This satellite will test how the pressure of sunlight pushing against its sails moves the satellite around. The closer to the sun, the better to test its solar sail technology, hence the reason for this mission requirement of a much higher orbit than the primary payload on Electron today.
Throttling down.
T plus 5 minutes 32 seconds, and our launch operator's next call out will be for the battery hot swap. Our rocket engine's pump is battery powered, and since it's been flying for a while now, its power source is starting to run low. So to keep the engine and the mission going, Electron's engine power system swaps to a new battery pack for fresh and continuous energy supply to the electric pumps. The old set of batteries will be discarded.
Hot swap successful.
And as confirmed by Mission Control, battery hot swap has been completed for the second stage Rutherford engine. Propulsion remains nominal, and the mission is continuing on its journey to that first payload deployment with KAIST and NeonSat-1. Now, of course, once NeonSat-1 is deployed, that is only the first of 2 satellites to be released on this mission. Electron is also carrying NASA's Advanced Composite Solar Sail System satellite that will be deployed at twice the altitude we're heading to now, from 5 520 kilometres above Earth to 1,000. To do that, we'll first need to repeat the stage separation process we completed earlier in the mission, this time separating Electron's third stage, or kick stage, from the second stage. That second engine cut-off milestone, which you'll hear called out at SECO, is expected at around 9 minutes into the mission.
The mission is continuing nominally. We have about 16% of propellant remaining. We're currently cruising along at a speed of over 21,000 kilometres an hour and approaching an altitude of almost 209.
We're coming up now to engine cutoff on the second stage, the last action this stage will perform for the mission. Much like with the first stage, Electron will power down the Rutherford engine on the second stage to allow the kick stage to separate cleanly. We time the engine shutdown for right as we reach that target perigee of 250 kilometres. Let's listen out for that engine shutdown and stage separation now.
SECO confirmed.
Stage 3 separation confirmed.
A great call from Mission Control. The second stage engine has turned cold and the kick stage has separated, ready to begin the payload deployment process. Now, this mission, of course, is a little different to a regular Electron mission, so here's a reminder of how today's two deployments will work. Now that the kick stage has been released, it will now go into a phasing orbit of Earth. Because it's been set into an elliptical orbit from its perigee, it needs to head around to the other side of the planet to an apogee of 520 kilometers before it fires up the Curie engine to course correct into a circular orbit. Now, once it does, NeonSat-1 will be deployed to begin its mission for KAIST, and that will be phase 1 for the kick stage.
Phase 2 will see it light up its engine again to perform an apogee raise to 1,000 kilometres, the target altitude for NASA's satellite. That apogee raise will bring the kick stage out of a circular orbit and back into another elliptical one. Here, the kick stage will do another half pass of Earth before the dots reconnect again at 1,000 kilometres, where it will light up its Curie engine for a third time to circularise its orbit before payload deployment.
Once that's done, it will be on to phase 3. The Curie engine will ignite a fourth and final time to undo its circularization and bring it back into an elliptical orbit. This orbit lowering maneuver will help to speed up the kick stage's deorbit, doing our best to keep space as tidy as possible.
The launch was Rocket Lab's 5th flight this year and the 47th Electron mission overall. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with the Science Report. A new study claims women with BRCA genes who get breast cancer within 10 years of giving birth are more likely to die. The findings, reported in the Journal of the American Medical Association, looked at data from 903 British women with cancer-causing BRCA genes and found that those who were diagnosed with breast cancer within 10 years of giving birth were more likely to die from the disease than those who were diagnosed later or women who had not given birth. The highest risk was seen among women with the BRCA1 gene who were diagnosed with estrogen receptor-positive breast cancer within 5 years of giving birth, and women with the BRCA1 gene diagnosed with estrogen-negative breast cancer between 5 and 10 years after giving birth. Interestingly, the same pattern was not seen among women with a BRCA2 gene. The authors say the results should be used to inform genetic counselling, prevention and treatment strategies for women with BRCA genes. New research suggests that the degree to which genetics influence autism could be different for males and females. A report in the Journal of the American Medical Association analysed data from a study including over 1 million Swedish children, of which 12,226 received a diagnosis of autism spectrum disorder. They found heritability of autism spectrum disorder, that is a measure of how well the trait can be attributed to genetics, was estimated to be between 10 and 12% higher in males than in females. The authors say the findings indicate there could be a difference in the underlying causes and prevalence of the condition and may not necessarily indicate a protective effect in females, but rather differences in genetic variances between sexes. An accompanying editorial says the findings are an important addition to the field of autism likelihood and so warrant further population research. Scientists have found that tiny plastic fibres of polyester materials are messing with the way organic matter is usually broken down on the seafloor. A report in the journal Marine Pollution Bulletin warns that the effects of these microplastics differed depending on the makeup of marine sediments, but they were always disruptive. The authors say polyester microfiber pollution is causing profound ecological harm by interfering with natural cycling processes in coastal ecosystems that are important for supporting life on Earth. Well, believe it or not, rabbits can and occasionally do grow horns. That's led to a major breakthrough in medical science. But as Tim Mendham from Australian Skeptics explains, these horny rabbits, for want of a better term, have also spawned a massive hoax, which has spread like wildfire across the American Wild West.
These are bunnies that appeared and they've been talked about for some time, in America mainly, and it probably gave rise to the jackalope myth of these sort of antelope stroke bunnies that are sort of around and appear every so often in the American Midwest. But what it turns out is that there are bunnies with horns, sort of. Okay, basically what they have is rabbits that have got some sort of papillomavirus, and that creates sort of fibromas on the skin which build up and they look like horns. I don't know how hard they are. I'm trying to look at the reports to find out how solid these horns are. People think they're not particularly dangerous, so it's unlikely. But these are confirmed animals, and they're basically animals suffering from a disease. But one of the most interesting things is it's actually led to people trying to find cures for cancer, because what these things are is actually the cancerous conditions that these poor little bunnies are suffering from. This has helped via various processes, not directly the ultimate researchers looking at rabbits, but the information that's coming out to the human papillomavirus treatment against cervical cancer and things like that, which has been hugely successful. The fellow who originally worked on finding the link between the rabbit and this papillomavirus has won a Nobel Prize for his work, and obviously it's been picked up by other researchers and leading to what we are seeing now. So these horned rabbits, which are real, have given indirectly a great medical benefit. About the same time as these horned rabbits first started showing up, took a rabbit body and an antelope body, I don't know where we got the antelope from, never mind, and put them together and said, look, this is a creature. And because of the excitement about horned bunnies, way back when, we're talking Depression era time, that suddenly this jackalope, which had been created, was given some imprimatur as being real. And ever since then, jackalope have featured in a lot of jokes. A lot of people have jackalopes stuffed in, well, a lot of people in the American Midwest anyway, have jackalopes above their bars in saloons, etc., and tourist industry galore, etc. So not the same thing as the horned bunnies, but perhaps inspired by them. So horned bunnies have created a very real and worthwhile cancer treatment, and have created a tourism industry at the same time.
I wonder if that's also the inspiration for movies like Donnie Darko, where the evil rabbit keeps appearing in his dreams.
I think that's a puka.
Sounds like the name of a chihuahua.
It's actually a Scottish myth, I think, a puka. But it's also, if you see the film Harvey,
yes,
Jimmy Stewart, that's a puka. That's a big rabbit too. But Donnie Darko is like a dark version of Harvey.
That's Tim Mendham from Australian Skeptics. That's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more space time, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.